Okay, let's get down to the crux of the matter. We generated our data flash logs. Now what do we do with them? We're over in documentation, copter. We're talking about first flighting, tuning, uh, configuring notch filtering. This is what we were doing with the test flights. We're trying to figure out our notch filter center frequency. Therefore, we jump over to here to do that. This is where we set up our pre-flight logging. And now after the flight, this is what where we're at right here. Post-flight analysis. Perform a regular flight, not just a gentle hover, at least 1 minute, and download the data flash logs. And downloading the logs, emission planner. You come here, click right here, download data flash logs. Mine are downloaded and cleared. You just download them all with this button or select some with a check mark and download selected, but I've already done that. So, mission planner, under setup advanced, press the FFT button and input your IMU batch log from that flight. That'd be advanced, FFT, IMU batch. This is the little 5-inch. Here's the generated logs. We're looking for peaks here. We can come in with our cursor in truth here and see that as we go right and left here, we can see the peaks. I'm going to call it 190. If we go to this one right here, it's right at their 200. I can probably call it, I think I'm going to call it 190 because there is some values on each side that is filtered. This would be the secondary harmonic here. Actually, yeah, at 400. My graphs don't match their graphs in the name ACC 0 here, but I got ACC 2, and then gyro 0 and gyro 2. And then these two graphs for me are just way different than the documentation. So here on the graph, it's possible to identify a significant peak in noise that corresponds to the motor rotational frequency. On a small copter, it's likely to be around 200, which we saw that. On a larger one, 100. Here's a 5-inch quad. They show it around 180-ish or so here. Here's with it attenuated. The top of the peak is at -10. -10 is up here. It's definitely attenuated down. Actually, the bottom of all of this noise is at -50. That's where the top of this now is. So it's been attenuated or pushed down. And their gyrographs, no, I don't have anything like that. There's. It's not my results. ACC1 and Gyro1, where I have 2 on that label, doesn't really bother me. This is what I actually have. Just looks a little strange for me. let's go back to the documentation here. 4 graphs are shown: ACC0, ACC1. I get ACC2, but that's just documentation problems. Vibrations at frequencies above 100 hertz may lead to attitude or position control problems. That might be why that little creature accelerated up yesterday. I think I looked at that telemetry data in the first one. It says a pronounced noise peak at 180 is evident. Smaller harmonic here. That's this graph we looked at. Note that the noise has been dramatically reduced by the low-pass filters on the sensors, but across a significant lag between the phases. I guess they're talking about these graphs not being perfectly on top of each other. This one is kind of, well, on top of each other. These two paragraphs don't make a lot of sense to me. Don't think they're well written. Notice that the noise has been dramatically reduced by the low-pass filters on the sensors, but at cost of significant phase lag that will have reduced how tight the tune was made. It should be possible to notch out the 180 hertz motor spike, this one here, and increase the gyro low-pass filter to 60 or 80 hertz to allow tighter tune to be done. I haven't seen anything about where those are controlled. Accelerometer path is not as critical since it forms an outer loop around the gyro-based rate PID controllers. Oh man, I think this whole sentence is talking about the logic inside the software, inside the program, that the gyro-based rate PID controllers in the actual code, the accelerometer changes is done in a loop outside this. This is taking place inside the accelerometer loop. It doesn't make it clear at all what they're talking about there. It seems to me like people trying to just talk up their intelligence or knowledge. So that goes over my head. Leaving its low pass filter at 10 does not affect the ability of the vehicle to reject disturbances quickly, which is the rate controller's main task. Again, we're back to this. Like I say, this whole paragraph just bothers me. And this one is improperly translated, because if we just increase the gyro low pass filter to 60 from 20 hertz without adding notch filters to decrease the motor noise, that will result in unacceptable results. It's not really even good grammar here. If we just increase the gyro low pass filter to 60 hertz from 20 hertz without adding notch filters to decrease the motor noise, this results which is not acceptable. Doing just the low pass filters just doesn't hack it, is what that's trying to say, in my humble opinion. So they're showing that here, that the gyro noise spike here at 40, bottom of it at like 70-ish, isn't really completely worked out by just changing the gyro filter. We do have this down below 50, so it's pushed down a little bit, but it's not pushed down enough. This text says it's increasing the noise. So we'll leave that one alone because I just hate this documentation. So we've gone through a little confusing things here, but we've seen that we're looking for this spike. And then what do we do with it? So here we get into notch filter setup. How do you do that? I'm going to break this video here just a second. So it is possible to filter some of the noise to increase performance and allow better tuning by activating the harmonic notch filters. See managing gyro noise with the dynamic harmonic notch filters for details. That's right back to where we were. That's this one right here in truth. That's going right back around to where we were. We were determining the center frequency. So technically we'd be down below this right now. This is your 4 or 5 types of notch filters, but this doesn't really tell us how to set them. So we'll just close this because we've got this open over here. For throttle-based dynamic harmonic notches, you will need some additional information from the logs if using a throttle-based dynamic notch setup. With the same log open in the regular way in Mission Planner and graph the throttle value. See tune throttle. So, okay, this right here is talking specifically about throttle based. So we're going to do this because there's a viewer who wants to go through this. That's probably not what I'm going to use, but we'll look at that. So let's go ahead and look back. Okay, with the same log, open it in the regular way in Mission Planner and graph C tune throttle 0. So now this is different from this. So we can close this. We can actually leave here because they're talking about coming over here and reviewing a log. And we're talking about this log. And this is the C tune. Throttle 0. And what did they want us to do there? Graph the throttle value. From this, identify an average throttle, hover throttle value, which will be used for the notch filter reference. It's also possible to use motor hover learn equal to in copter and read off the value of motor thrust hover, or motor thrust learn in quad plane, read off the value from quad motor thrust hover. This gives you a hover motor frequency and thrust value hover thrust. Note that learning of hover thrust only occurs while in altitude controlled modes with no pitch or roll angle. Therefore it should be done in calm wind condition with no pilot stick input for at least 10 seconds. Okay, let's forget the motor hover. Let's go and look at that graph, see what we got there. and I need to show point values. So this is time. Something did. This is where altitude hold came off. I don't know if the center of this thing is where stabilize came back on. This is where I put it in altitude hold. I don't know if the leading edge of this is where it was taken out, but we do see that big spike in throttle there that caused that thing to go crazy yesterday. And what are they telling me to figure out here? So this is time across the bottom. Minimum max. It doesn't tell me what these numbers are over here. But you're looking for an average thrust value. Well, I guess it's what's shown in white right there is the time, comma, and the value. So an average one right here looks to me like it's 0.04264615. I need to write that down someplace. Oops. It went away. Yeah, right in the top here looks kind of like 0.04. Man. 46717. 46717. Ah, man. How about that? $0.4206706. Man. Wish that would stay. 0.04. Damn it. 04034062. Okay. I think that's what they're telling me to do there. Graph the throttle value, C-tune, copter, quad tune, quad plane. From this, identify an average hover throttle value, which will be used for INSH reference. This is going to take me to the complete parameters list, but I just want to see what they're talking about there. INSH harmonic notch filter reference. This parameter is for advanced reboot required. A reference value of 0 disables dynamic updates on the harmonic notch filter, and a positive value enables dynamic updates on the notch filter. Okay. For throttle-based scaling, this parameter is the reference value associated with a specific frequency to facilitate frequency scaling in a harmonic notch filter. Sort of understand that. For RPM and ESC telemetry based tracking, this parameter is set to 1 to enable. Now then, I'm not going to use, we're using throttle based, not RPM or ESC based, telemetry based notch filter. If you're using these two, the parameter is set to 1 to enable harmonic notch filter using the RPM sensor or ESC telemetry set to measure rotor speed. But it's a little bit different for throttle based. Sensor data is converted to hertz automatically for use in harmonic notch filter. The reference value can now be used to scale the sensor data if required. For example, RPM sensor data is required to measure helo motor RPM. Therefore, the reference value can be used to scale. So the range is from 0 to 1.0. So that 0.03 stuff I was reading seems pretty understandable that it fits within that. Boy. So this talks about after you set up the notch filter, then you would do a post-flight to see how your graphs changed. Okay, so what we want to do here is go back. We're looking at doing throttle based for one viewer. I'm going to try to use mode 4. Or if I have to, I'll use telemetry based. So what we now need to do is look at these notch filter types. So let me find that information. Okay, we're going to keep this page here, but I'm going to come back over here. This isn't very understandable. The documentation kind of stinks here, but it talks about the types of notch filters here, why you would want to use more than one. Talks a little bit about the FFT mode, doing double or triple notch filters, which I don't recommend. But if you click next here, and this really isn't understandable in the documentation, you actually open where you're going to go through the different types. Here's throttle based, notch setup. Click next, we get a page for RPM based and how to do that. Click next, we get an ESC telemetry based notch setup and how to do that. And then in-flight FFT based notch setup here. That takes care of our 4 different, and then this again talks more about checking all of that. So let's go back. Oops. ESC based, RPM based, throttle based. So with mode 0, then notch filtering is turned off. You have mode 1, 2, 3, and 4 different modes. So that's what we're going to be talking about right here. Oops. No, right here. So the first one is throttle-based dynamic notch setup. If you do not have ESC telemetry or an RPM sensor and are not using an autopilot capable of using the in-flight FFT mode, then throttle-based center frequency control is best. So you're going to set INS notch filter mode to 1 right here. 1 throttle position based. In order to configure the throttle-based dynamic harmonic notch filter, it is important to identify the motor noise at the hover throttle level. To do this, we need to use the batch sampler to obtain logs for analysis. You're back over here to measuring with the batch sampler. This is what we've been doing. That's why we did our flights. Once this is done, the center frequency of the notches can be set and other parameters configured. Set first notch filter mode equal 1. So that's this parameter. See if I can scrape through this one or the other of these. Nope. So INSHNTCH. Oops. Oh, that's the 7-inch that's plugged in, not the 5-inch. Don't think it'll be matter. INS underscore. And what was it? HN horizontal notch. HNTCH. 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 Okay. So here we are. It says the default's 0 now. Oh, this is the 7-inch. I'm going to have to change that over. The 7-inch has had all this done to it. Just kind of coming back and looking and seeing that the 7-inch was set up correctly. So I'm going to back out real quick and change my platform over there. Sorry about that, guys. So now I'm actually connected to the 5-inch platform, which is the graph we were looking at, not the 7-inch. So INS underscore HN yeah. It's never been enabled on the 5-inch. HNTCH. TCH. Horizontal notch. That's the first one. 0 disabled is the default, not 1 enabled as the no, I think it was the mode. Once I enable this, the mode will change. So I need to change this from 0 to a 1 to enable the first notch filter. We'll write that out. And we do need to refresh the parameters. And now we see all of these, which is the full parameters after it's enabled. Right here, this enabled. These are the default values for everything, including the mode, which is a 1 for throttle based by default. That's the one we actually want to set up on this example. I will come back and set it up differently. Okay, set it to a 1. Oh, that's mode, to set it to mode. Set hitch enabled to enable that notch filter. We did that. Here we enabled it. We didn't set this one to a 1. That's the default, so that's why that's there that way. INS hitch reference to hover thrust to set the harmonic notch reference value. Hover thrust reference to hover thrust frequency to hover frequency, and the bandwidth, hover frequency divided by 2. Oof. And then set notch filter FM rate to the percentage of pitch frequency that you desire the notch frequency to track below hover throttle. Okay. Okay. And check the performance of that filtering after setup by doing another post-filter configuration test flight discussed in the batch sampler section. Okay. Got these two taken care of. INS notch filter reference. This one here. A reference value of 0 disables the dynamic update on the harmonic notch filter, and a positive value enables dynamic updates on the harmonic notch filter for throttle-based scaling. This parameter is reference value associated with the specific frequency to facilitate frequency scaling of the harmonic notch filter. For RPM and ESC telemetry-based tracking, this parameter would be set to a 1. We've already seen that in the documentation. Sensor data is converted to hertz. Reference value also may be used to scale the sensory data if required. Boy. Okay, so INH reference, the frequency, this one, and the bandwidth. Half the base frequency. So this is 80 for the frequency. That is half the base frequency. Boy, I hate this stuff. So reference frequency equal hover thrust. And that's where we looked at C-tune, and that'll be used for INS harmonic notch filter reference. I'm not going to do this learn part. So INS H reference is that 0.04 stuff. Yep. So in my opinion, this should be set to that 0.0446717 that I wrote down, like that. Okay. The frequency equal the hover frequency. I honestly think that one should be that 180-ish that we saw. Okay, I'm going to come back out of this for a second, go back over here. I think that is this one. What did we decide for this? We decide we'll set it to 187 right in here. And we'll set it to 200. INS underscore HNTCH. I think this should be 180 or the 200, and therefore this one should be 90. That's half of that one. Oops. Yeah, the bandwidth would be half of that. So what you're going to do there is you're going to be looking 90 hertz on either side of this center frequency here. And set highness harmonic notch filter FM rate, I'm going to call it, to the percentage of the frequency, percentage of that 180 that you desire the notch filter to track below horizontal, below hover throttle. So it's a percentage that you desire. This right here. The minimum ratio below the configured frequency to take throttle-based notch filter when flying at throttle level below the reference throttle. Note that lower frequency notch filter will have more phase lag. If you want throttle-based notch filtering to be effective at a throttle up to 30% below the configured notch filter, then set it to 0.7. The default of 1 means the notch filter will not go below the frequency in the frequency perimeter here. Well, I could leave it at a 1. If you want the throttle-based notch filtering to be effective at throttle up to 30% below the configured notch frequency, then set this perimeter to 0.7. That sounds good to me. Just a little bit there. Okay. At this point, I think we're set. Check the performance of the filtering after setup by doing another post-filter configuration test as detailed in the batch sampler. Ooh, we're supposed to go fly again. Yikes! Especially on that little 5-inch. So we're going to write these parameters out. We're going to save these to the hard drive for the little 5-inch. But we're going to save them as temp right here. And I guess that one's ready to go fly again and see what that does with the notch filtering. So I need to get my batteries charged and everything for that. Because this video is so long, I'm going to break it here and publish it. It's already 40 minutes. This is a terrible subject. You can see again notch filter on, 180 for the frequency. Set that to 7 because I did want some configuration below throttle. 90 for half of this, and this was that value that we pulled out of the graph. All right, guys, thank you for now. It'll take me a while to get ready to fly today, so I'm going to go ahead and render this and publish it. Thank you again.